exactly the problem. I didn't write too much of one question.
Okay, welcome everyone. How are you doing? Amazing. I like that. Is there, you don't have to share, but is there anything that's super amazing?
It's just a great day.
It is. It feels a little more like fall today, doesn't it?
Yes.
It feels like we may have it. Yeah. Okay. Well, today is our fourth time getting to meet with each other. And I'm excited because we are going to cover stress and strain. How much of stress and strain do you cover in statics? Any? I would say none, right? Okay. I think sometimes the class gets to talking a little bit about stress and strain at the very end. Okay, so I expect that what we cover today is going to be a little bit new to many of you. But we already talked about pressure a little bit in this class. Okay, we did. And over the summer, there was a devastating accident that had a lot to do with pressure. Any ideas? Right? Yeah, right. Okay, so there's a certain submarine doing exploration. Okay, and it was underwater, and it was under a lot of pressure. Okay, and I guess there's probably still ongoing investigation in terms of what happened, but simplistically speaking, it was under a lot of pressure, and it broke, and it was catastrophic. Now, we will talk about pressure vessels later in the class, okay? And we'll talk about the stress and the strain in the walls of pressure vessels. Normally, our pressure vessels are pressurized from the inside and not from the outside, okay? So that we have the walls in tension. What is difficult about submersible vehicles is that it's going the opposite direction, and so there's the chance when it's under compression that long faces can buckle. Okay, I mean they can fail as well, all right, because of the stress in the walls, but they become even more difficult. Now, today we're not going to really talk about vessels or objects that we're pressurizing, and we want to figure out what the stress is circumferentially or axially might be in that structure. That will come later. But we will come up with some ideas and some ways of expressing stresses and the associated strains. Okay. Now, what are the units of stress? I think we talked about this before. What are the units of stress? Okay. Yes, Zach.
Pascals.
Yeah, so let's start there, right? Because, on this last assignment, I think people started to realize stresses stink sometimes. Or not stresses, units stink, right? Or they can be annoying, right? So units of stress. Okay, so pascals. What are some other ways we might express stress? And then we'll get into what these units mean in a second. Yes?
PSI.
Yeah, PSI, right? And you're like, okay, I've heard these a lot, right? In the US, if you inflated the wheels, the tires on your car, right? You heard PSI. right? And you're like, okay, is 30 psi a lot? I don't know, right? Any cyclists here, road bikes? Yeah, what if you're going into a competition, which I would never do, all right, but what is the typical pressure that you pump up your tires? Okay, yeah, and if okay, so 90. Anyone want to go higher for road cycling, for Prestavals? Will you ever go higher? Yeah, so like it goes. So those tires are rated up to 120 psi often. Okay, and it's dangerous. It can be a little bit dangerous when you're just riding around recreationally and you overinflate your tires. So one time I had my tires. I was like, I'm gonna be cool. I'm gonna like put them up. I'm gonna feel like I'm really fast. And I had the tires like at 120 psi, and I had to stop suddenly to not run into a car at a stoplight. That one was my fault. I wasn't paying attention. I slammed on the brakes so hard, and the tires were so amped up, I guess you could say, in other lingo, right? That skidding, that shear that I put on the surface of the tire actually caused it to burst slightly, so that the tube was coming out of the tires. So you got to be careful with that. All right. What are some other units that you might say for stress? Yes. Bar. Okay. Yes. Usually, when you're talking about bars, what are you talking about? Not Friday or Saturday nights, but like what?
Pressure.
Yes, we're talking about pressure. Yes, and atmospheric, right? So the weather often, right, is they talk about it in bars, right? Okay. I don't know. Maybe that's hey, you never thought, what's it like? It's a great weather we're having today. It's so many. Anyway, never mind. Okay. So other units that you might find? Yes.
Newton per meter squared.
Okay. So Newton per meter squared. All right. Yes. Okay. Okay, good. Yes. Torque. Okay, I was like, oh yeah. Yeah, torque. All right. Often millitorr is what they're doing under vacuum systems. Yes. Inches of mercury. Okay, yeah. Good. Yes. Atmospheres, yeah. All right. Good. Okay, and these are, we're getting here, these are really units of pressure, okay, that we're getting into, that we're more familiar with, right? And we have an idea of what it means to be under pressure. So, the simplest case that we will deal with is axial loading and axial stresses or normal stresses in a bar. Okay? Those are the simplest cases. So if you've been watching the videos or not, right, you're starting to see that we can describe the force, all right, maybe with these vectors, like so, with F or P or something like that. But then if we know what the cross-sectional area is, okay, we can come up with what the normal stress is. Okay, and I'm going through this kind of quickly, all right, and I think I do a better job in the videos, but this is kind of just to give us an idea, right? And if I were to look at this face, right, what I've essentially done, so I'm looking at the face, okay, and I've got some force coming out, and I'm breaking this face up into lots of little small areas. Okay? And if I look at the vectors coming out of this face, there could be all these little DFs. There's all these little small forces coming out of this face. Okay? And if I have these small little DFs and I have these small little DAs, okay, I can say I have some stresses over this face. Right? And for our intents and purposes, we're just going to say that we can approximate that as that. Okay? Again, force divided by area. Okay. Now, we will have the opportunity to look at different planes and come up with different ways of describing the stresses on these planes. Okay, so let's do this. Let's take another one of my poor drawings. Okay, and let's say that we've got the forces coming out of here. Let's say that our coordinate system is the following. We're going to say we have z upward, we're going to say we have x this way, we're going to say we have y this way. So z coming out the top, x coming at you, y going to the right. If I take this slice now, if I say, okay, I'm gonna look at this plane. Okay. How could you describe that plane on that right side of this object, which we have a force coming out of? Just in terms of letters, what kind of plane is that? Think to your multivariable calculus days. All right. What kind of plane is that? I can think of two ways to describe that plane. You could probably think of them. Yes, Zach. Okay, yes. So you could say that is a ZX or an XZ plane. All right, so that's fine. So this is an XZ, okay, or ZX plane. All right, on that side. What's another way you could describe it? You might say, well, any others? Yes? Okay, y equals 0. Okay, yeah. So you could say, yeah, a y plane, right? Because y is coming out of it. Yes. And you could call that y equals 0 if you want, and that could be a y plane because you have a y vector coming out orthogonally, right? So those are kind of the two ways that you could describe that plane. Okay? We are going to have a nomenclature, right? Another convention, not a party, but another convention that we use to describe the state of stress in an object, okay? With respect to its reference frame, okay? Or its coordinate axes. And people will say, oh, reference frame is not the same as coordinates. That's true. That's true, all right? Let's say that we draw now a cube, okay? And this was kind of a cube, but not really a cube. But let's say that we take a little cube inside here. Okay, a really bad drawing. All right, so I've got this little microcube inside my structure. This microcube we can think of as what we call a material element. All right, essentially infinitely small. Okay. When we're doing this. So lots of little DAs, lots of little DFs, all right? And we're going to use it to describe a state of stress. So if I take that little element, and I try to draw it very poorly, like that, okay? And I use the same coordinate system that I've been saying we're going to use. I have a z coming out that way, I have an x coming out this way, and I have a y coming out that way. We can begin to come up with a way of describing the stresses on any of these faces. Okay? And if x is coming out of the face, or y is coming out of the face, or z is coming out of the face, we call that a positive face. All right? So this is the positive over here, that's the positive x face. On the back side, which I can't see, that's the minus x face. This is the positive y face. This is the positive z face. The positive z face is down, or the negative z face is down here. All right? So what we will often see is a 2D representation. So it's only going to it's often, not always, and we will do 3D problems, or we'll call them 2.5D problems, because we're often visualizing in 2D, but then we have to like twist it a little bit and think in 3D. All right. What we do is we say, okay, this is a face, and now we're going to draw some directions on it. Okay. So, for example, if I take this face right here, that's the x face. Okay. So now I'm going to draw the x face. Remember, x is coming out of the board. So now my coordinate system is y over here and still z up top. Okay. X coming out like that. So this side, all right, even though it's only a line, all right, it does have some depth into the board. This side is what we call a y face, all right? This side is what we call a z face. This side is what we call a negative y face, and this is what we call a negative z face, all right? And if we start describing the stresses on this x face, all right, we can do it with the following. We have the normal stresses, like we were talking about here, but we also have something called shear stresses, okay, which are described in the notes and in the video. So this is the standard way of drawing this. And we'll get into what this means. Okay. How many arrows, how many purple arrows do you see there? Okay, yes, that's a lot. Okay, now, the way we describe each one of these arrows is with subscripts on a sigma. So, this is sigma x, I can't even do it. This is on the y face, so this is sigma y, y. How does this work? If you have a stress, the first subscript is the face. The second subscript is the direction. Okay. So, on this sigma y, y, all right, this is on the y face in the y direction. What is this one going upward, this purple one? Up here, what's this one? I heard it. Someone snoring? No, right? It's Z. It's ZZ, right? It's sigma ZZ. All right. Okay. What is this one? Yep. Who said that? Owen. All right. And this one? Yeah. ZY, right? Okay, good. Now, I kind of lied a little bit. You'll not see a true mechanician write things like this, okay? But we'll get there in a second. Okay, we're going to take a little bit shortcut. All right, so this one down here is a little bit trickier. Okay, this one over here. All right. Okay. This one down here, right? This is on the negative Z face in the negative Y direction. Okay. And this is on the negative Y face in, oh, we already did that one. Yeah, in the negative, this one over here. This is on the negative Y face in the minus Z direction. Okay, did I do that right? I think I did that right. I probably messed it up somewhere. Okay, so, yes, what did I mess up, Raj? This one? This one? No, this is on a Z face and it's going Y, so this is sigma ZY. The one on top is sigma ZZ. Okay, all right, no problem. Say that again.
The one should be minus y minus z, and then the one minus z minus y.
So this, what's this arrow? This is a minus Y face, okay, and it's in the minus Z direction. All right. Good. Are we all together, like one direction? Would Harry Styles be happy? All right. So, like, let's think about what we can do to simplify this notation. Okay. So one, if we write out sigma y, it's a little bit repetitive, so a true mechanician will just write sigma y. Similarly, sigma zz can be written as sigma z. Okay? Now, if you go into the notes, you'll see that sigma minus minus is the same as sigma plus plus. All right? So, and this has to do with equilibrium. Each of these micro material elements cannot be moving around. We're still doing statics, right? So, if I were to look at equilibrium in the y direction, right, and in the z direction, and I look at moments about x, right, I need these to be satisfied. Okay? So in order for that to happen, if there's one force associated with a stress, right? The other thing to remember, right, is if I have a stress and I have an area, I can figure out what the force is. Right? So when you do equilibrium, okay, so right now do not add the stresses to each other. But when we do combined loadings, we will add the stresses. If the stresses are in the same direction, acting over the same element, you can add them together, okay? That's niceness. But when we're thinking about equilibrium, don't think about stresses in equilibrium. We still have to think about micro forces balancing out. We still have to think about micro moments balancing out. Okay. So these are what we do here, and we even go further, and we'll say that sigma minus z can be written as sigma z. We'll even go further, and we'll say that sigma minus y can be written as sigma y. Okay, and then there are these other terms, sigma yz, sigma zy. All right. We don't write it this way. Okay, we don't. All right. Y and z are not the same, and so we introduce another variable to make it more interesting called tau. Okay, tau is what we use for what we call a shear stress. Now, what is a shear stress? Okay, what is a shear stress? What do you guys think of when you think of shear stress? Yes?
Scissors.
Huh?
Scissors.
Scissors, yes, we're gonna do a little bit on scissors when we do some beam stuff. Like you're like, beams and scissors? What in the world? Yes, scissors. Well, what's happening with scissors? Why do you think what's
One coming up, the other one going down.
right? There's this sliding action. All right? And we will tell you why is it often easier to cut a material with scissors than by pulling it apart.
Smaller area.
Well, yeah.
Higher pressure.
Okay, so, yeah.
Is it concentrated?
Okay.
Wait, can you repeat the question?
So, why do we use the scissors? Why does something cut? Yes. There. Okay, yeah.
Because you get a more effective shear stress.
Oh, it's as if you yes. Okay, so we're kind of doing circular reasoning here, all right? What happens, we will go through this in this class. We will talk about what is an equivalent shear stress in terms of normal stress. And in many cases, what you'll see is that you need only half the shear stress that you need of the normal stress to cut something or to break it. Okay? So often, we try to do things in shear. We try to break materials in shear. Okay? We slide, we make the gap very small so we can get very high shear. Yes?
Is that because there's two sides coming up, so that?
Yeah, so we'll get into this a little bit more, all right? Materials, the ductile materials, they fail more easily in shear, whereas the ceramics, the brittle materials, that we care more about normal stress, okay? But we can come up with equivalents between these, and we'll do this later in the class, all right? Essentially, it fails in shear, and that's circular reasoning for now, okay? And if we got into the molecular level or whatever, we could say, okay, there's some sliding of the grain boundaries and stuff, and that allows us to get this more easy failure, okay? So shear is often what you try for, right? If you go to the machine shop and you're doing sheet metal, right? You have the big shear. You go in your kitchen, you have scissors, right? So you often want to try to get things to fail in shear. What is it though? It is a stress that is acting along the face, not normal to it. And you're like, well, duh, that's what you just drew. Yes. Don't be scared of it. Don't be scared of it. And if you're a fluid mechanician, you love shear stress because you're not getting any normal. Or you're not really. You're not going to get any elasticity. I should be careful. You can have pressure, you can have hydrostatic pressure in a liquid, right? But for Newtonian fluids, right, we care about viscosity, and viscosity is based on shear stress. Okay? So, similarly, we can write that sigma zy is tau zy. And then we can go one step further and say, and if you look in the notes, you go through this element better not be spinning or accelerating, or better not have angular acceleration and spin. Okay, and for that to be the case, these have to be the same. So typically we just write tau yz. Okay? And also from equilibrium, so this is based on equilibrium of moments, we can say that these are also the same. Yes, was there a question, Daniel?
Yeah, so if an example for shear force would be scissors in a paper, for example.
Shear stress, yes.
Yeah, and then, so what would be an example for normals?
Oh, well, normal is me trying to rip the paper across like that. Okay, because I've got my force going on the same, it's coming out of the plane. All right, that's, and I'm not very good at that. Okay, and also, yes, you're right. You're trying to, one thing you said, right, is that you get a lot of force with the scissors. All right, from a mechanistic perspective, you do get a lot of force per small area. So you can also, with a scissors or a shear, crank up that shear stress really high. If I'm trying to pull this apart like this, I've got all this area, right? But if I go this way, I've got a little bitty area that I'm working on, and I can get all that force, so I can get high shear stress. So that's another reason why scissors. All right. Okay. Let me talk about one more thing, all right? Because it's going to hang us up, and Praj told me I have to talk about it. And then you can get on to your other things. We'll do attendance, and you can get on to working on problems. So this is session 2, all right? And there was a bit about trusses, but no questions on trusses, all right, until now. All right, so now I just want to go back and talk about trusses. With trusses, and if you want, you can go review chapter 6 in the Hibbler Statics book, right? The methodology, well, there are actually kind of 2 methodologies, but in both methodologies, the first thing you do is external equilibrium. Okay? So what does that mean? In this simple truss, it means that we draw out the forces that are acting on the pins in the truss. Right? And this one is a roller. Do you like my roller? Not really, probably. But anyway, my roller's nice, right? It almost looks like you're rollerblading up and down the wall. Okay? So, and then this is fixed, all right? So the roller can only apply a force out of the wall. Cannot apply a force vertically. But the pinned joint here, okay, where this is attached to the wall, this is able to apply a force vertically and horizontally. And then there's a force out here that's acting downward. P is given. Okay? But I don't know these other forces. Now, remember we have conventions. Conventions are great for internal meetings, all right? For internal descriptions within a structure. But you don't need a convention to talk about what's happening outside. All right? Maybe that's a way to remember it, right? You don't need to have a convention to talk about what's going outside the meeting, all right? Anyway, maybe that doesn't work so well, all right? But for engineers, we do care about what's happening globally now, all right? That's part of being an engineer in today's world. But anyway, we digress. I can pick these reaction forces to be either in or out of the structure. So I've picked them using my best guess here. Okay. Then, after doing equilibrium here, I have a choice to make. I can use either method of joints or method of sections. Okay. And if I use method of joints, what I have to do is write out every single joint and the forces acting on those joints. Okay. Now, again, I can take some guesses in terms of whether or not they come out of the joint or go into the joint. All right. Except, well, P has been drawn out of the joint, so I'm going to probably want to keep that as it is. Okay. And then the external ones, I also kind of need to keep them straight, or I got to keep them as I've drawn them. So AX is going this way, so I'm going to draw it out that way. AY is going up, so draw it that way. Okay. But then there are these forces on these members, and if, all right, the force is coming out of the joint, okay, that means that that member, okay, if it's coming out, that means that that member is pulling on that joint. And so there has to be a reaction force that's putting that member under tension. If the force is going into the joint or into the pin or whatever it is, then it's going to be a force, internal force in the member in compression. Okay. Then, if I use method of joints, like I've done there, I come up with a bunch of equations using equilibrium. Okay? So, look, joint A, this is just getting all this stuff together. And I have two options, right? I have equilibrium in the horizontal direction, which is what this first equation is. I have equilibrium in the vertical direction, which is what this is. And then I can attempt to solve for relationships between the internal forces and the other loads that might be on the system. And I can do this. Essentially, it becomes an algebra problem from here. Okay. And so you do the algebra and you can solve for the force in the first member, which is this one. That's equal to 0. Force in the second member, that's equal to P. And the force in the third member, which is equal to square root of 2 times P. Now, if you want to shortcut this, I've provided partially completed code such that, okay, well actually I've provided completed code so you can calculate the forces in the members of this particular truss. Okay, if you run Colab. But if you need a stress, if I need a stress in this member or in this member or this member, member 3, which is the question you will have. It's behind door 3. It's this one. It's a 2-force member, so it can only have a normal load. So it can only have a normal stress. It can only have an axial force going through it. That's what we say. This is a 2-force member. So once I've calculated out the force in that member, which is square root of 2p, then all I have to do is divide by whatever the cross-sectional area is of that member. Okay. Now, in the homework I say, go ahead and use the Colab so you get experience with Colab. I'd love for you to use the Colab and ask me a question about it. But those of you who are practical, all you're going to do is you're going to say that it's F3, and I'm going to divide by the area of the cross section, and I'm going to give you the normal stress. All right. So, if you like, try the Colab, and then divide by the area. Note that this is giving, like the code here is using some linear algebra, which is not a requirement here for the class, and you can essentially set up a linear system of equations okay, that then solve for these internal forces, and it spits it out in this array. This one right here is F1, this one right here is F2, this one right here is F3. You probably just forgot that, but that's okay. And so to get these, you have to use a nomenclature which you can find in the session 4 Colab, where you do x bracket 0, x bracket 1, x bracket 2 to access these forces. Okay. If you don't want to use the method of trusses or method of joints, you can use the method of sections. Method of sections is nice because you don't have to write out an equation for every joint, but you don't get all the information. So there's a trade-off. But method of sections is cut, draw a line through the truss, then you've got your exposed internal forces, just like you would section a beam or a bar. And when you do that, you can then solve using equilibrium, like you see here, and you can potentially get the answers for F2 and F3 very quickly. All right? Depending on what you're trying to do. I wasn't able to solve for F1 here. Okay? I don't know what the force in member 1 is, but I do know what the forces are in members 2 and 3, because those are the ones I got sliced. What if I want member 1 using method of sections? Well, then I draw another slice, and I can get equations for member 1 and member 2. Any questions? Okay. So, before some of you go, please take attendance. All right? Let's pop that over. Whoops, that's not what I wanted to show. Hold on a second. Hold on a second. Let me see if I can. Hold on a second. Hold on, let's just do that.
Professor, Canvas says that there are issues with the Rutgers website.
There are what?
Issues with the Rutgers website.
I don't know what to say. Are there issues?
I don't know. It says
Okay. Well, if there are issues, I wish us all luck in resolving them. I don't know. All right. Okay. Okay, so go ahead. Afterwards, get started on the problems, and Raj and I will walk around. And those of you who have finished the assignment already, please feel free to help answer questions that others may have. All right.
No, but usually like it's like upgraded. It doesn't matter.
Okay, but not so fast. Okay, that's where, so that's where, no, that's where we hold it simplified. And now we have to. Okay, so we have, right, this is first one. That's one.
No, it's what?
This force that applies to action. Now, force that you
I need to order that. Not work for me. I clearly it's like 6 attempts. So I haven't seen a lot of my problems I work at. And I know it's so stupid, but it's not good. So many classes, I just really work backwards.
That's how much the bar at this end is going out, and how much the bar at this end is going out. So you're looking at the top, but it's the end So you have to keep track of all So what we can do is we can write out expressions this source, right? We have the same thing, but right? Now, I can say this
Six type deal. I'm getting like a 10 to 6 type. Well, I mean,
And once we've done that, we can say that there's a small angle approximation. Sine is approximating. And you can plug in from here. Right? Okay. And all right.
I got some,
They need to plug in so you have multiple one is this, right?
so,
From here. Right. So I can plug in here. And then I can go back to over here. Plug this. Then we can solve the
yeah,
data.
that's what I'm saying.
Once you solve the data, then, alright, then we have an adjustment data, and then we can solve the forms. Plus the delta 2 plus the rotation times L. Delta 1, we don't care about it. Because it's delta 1, is you do the delta 1 for delta 2. Sure, but use delta, but you need
Delta one is
no, delta 3. So delta 3 No, delta 3 is this. Delta 1 was back here, delta 1 was how much this on the left. I gotta go back to the side. What do you mean? Yeah, so there's, we go through this, there's the website. Engineering dash.
Oh, it's a separate, it's an entirely separate. That's why you think
I don't know.
Yeah.
I feel so.
So, it's the force is the same on every sector.
Understand.
So, I didn't have this. Even if you have two materials, right? I have one wall. There's two separate materials. There's two separate springs, but the springs and series of the force is actually the same. But the information in each of those numbers.
That's just like
Sure. Yeah, so that's one way to do it. Well, there's two ways. There's one way. But yes, this is it. And actually, I did it. Okay, alright, so go ahead.
Oh, it's just like
But then if you like are pulling, you can add that displacement. You can add that, right? Or you can create a displacement that also. So, let's say that, right? If I'm interested in displacement, just so. Then I want to figure out what the contribution where I'm just saying, okay.
Yeah, you right. It's just not gonna tell you if we're doing fantastic. Yeah, besides me,
So with F1, there's another way to do it, is to say, I want to go to 60. And then multiply by the J. Okay. But another way, so one way to do it is say, all right, so F1 has 20 on this side. And copy the rest of it go along to the right. F2 did not correspond to the same. Right? So F2 is not normal.
it just has bad
And three is actually with all three numbers. Right? But it's so F3 right?
like you figure out what they want to do.
I don't think I can see it. Oh, when you were taking
Right. So then these are all something called delta 1, delta 2, delta 3.
I'm wondering, so now I'm saying, you're always saying,
Alright, so you're adding the that's one of the other way to do it. The other way to do it is to slice it, figure out what.
I don't know why.
I think it's just the way it's like,
So if you have slice there, then open up the left. Okay. What do you mean?
Yeah, I work.
Tell me the next one. I live,
No, thinking immediately about Osaka.
yeah, I also lived there for 10 months.
What your name is?
Myrtle is my definition. And, like, that's in the role, definition. Because,
Yeah, the hell.
like, it would mean something better, but then, like,
It makes
it
it
would
in
be,
your,
yeah,
in the list.
yeah. Things don't really translate well from people to
Did you do?
It's in it.
You finished what you
It's like,
Yeah. This one is like it. Because this is really not usually what happens is classes you do it anyway. How you doing? Yes.
The rest is from the exam. If they did the work,
Okay.
at the exam, it's
So,
like 8%, they got from the exam.
And then you're done. The efficient engineering, good. The efficient engineering, very good. And what, yeah, very good. Good, pretty good.
Doesn't know it.
So the output of four. So maybe turn on in. So what is? Yeah, right, so now we can do is we type stress equals. This is a
No.
We just have to like,
What's he doing?
And then now we're gonna do five. Now we're gonna do
I didn't know
now what is the five? What's the yes, pi squared. And just have a diameter, right?
Yeah.
Move that way, or you can do pi right over that way. Any way you wanna do it, right? So, pi, then icon is NP dot. NP dot. NP.
No, I didn't.
And then you
Yeah.
d squared. So d squared is not actually done with a caret, it's done with capital D. So these two asterisks, yep, it's divided by 4. Now, you're gonna put a parenthesis. Now, everything was good except that. Yeah, so this, you be given, because I think, even though it says centimeters, or maybe you put it. Okay, so, yeah, so this is a mistake. So now we're going to set it at 0.01. Okay, so another thing, we gotta go through talking about. Now we are. Now we are. And. Okay, so here, okay, it's kind of like that level of living, right? So I had this, put in the center. There's no crack. Alright, then, so that's the air, that's the B. I mean, you can leave it in terms of syntax, the same thing as you can for it. So this is when it's not that you figure out the fourth and then so that I will put out just bracket. dot. They're calling NP first. NP dot. Good? Okay, and then, alright. Actually, I don't want to run specific, I want to be divided by the whole area.
Yeah, you.
Okay, we're gonna add another one. So that's fine. Okay, so then, we're gonna do it this way. The overview now, it's not in the Python, it's not there, two X. The brackets, if the parentheses are good, then try running it. Oh, okay, so now the other thing is to run this at the very top. Now we'll run it, not try. There you go. So we'll have it run down.
Yeah, she makes us. No, it's actually.
Okay, so this is section 4.
So, what language is it?
This is the oh yeah, yeah, okay, I got it now. Right here. Okay, so there's an average. There's one that has cells. Okay. There you go, try that. Multiply by, divide by. And also be careful with that. Okay. Yes. Okay, so number 6 is okay. Has.
Yeah.
So, alright, so that if it's lower equal, right, but nonetheless, we can go through the math, alright, or the mechanics. So where are you guys, where are you all right now? Okay, more explicit. Okay.
Okay, kind of.
Okay. 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 Okay.
Well, I'm getting
Okay. All right. So, where are your expressions for?
Like he asked if I did it.
Yes. So let's look at the all right. We start up here. So, where do you want to start?
Yeah.
What's going on? So.
So
You
now
have-
adding it, 8 is better. Because as you said,
Okay. hold on, so when you're using one of those numbers, so you're gonna go to what? Oh, okay, so I would go the other direction. I would convert everything to units and everything to meters. Alright, because that way, you keep all the units, you keep everything as standard. Alright? Yeah, if we convert it to millimeters, you convert it to kilometers. Then it gets, then it can get a little bit. So first try that, right? You want, you know, you write everything out, but you want essentially write it in meters. But the final answer is we obviously want it. Now, can I just say one other thing? Why don't you go ahead and use the COLA? So the COLA, we pull up. You go to the website, you go to session 3.
Joe,
No, on the website, So that's the slide, I'll go back. That's on the website. Go back. So the first thing you want to do here is you want to run this cell. Right there, you get it. So we go to session 3, so go down. So the first thing you want to do is you want to run this off. And then after so now we're gonna go down. We're gonna go down to the top.
here I should be able to get
This one. This one has a rotation. And then what you can do is you can plug in the numbers that you were given here. Okay. And you change those numbers to run. That will save you some calculation.
So I'd love to comment on one of the questions from the last class, because I remember we were talking about optimization.
Oh, yeah.
Because then I forgot to fill out the attendance, so I'll have another comment after. Does that comment indicate that I was here and participated?
Can you send me a message, one more message, and
That was all, that was it.
not mostly a comment, send me an actual
It's already
message.
there's ET6, it's already.
Okay.
There's nothing, if it's
So,
100, it's
I'm
no
gonna
way,
put that.
for your first changes. No. If I go.
I don't know, it's just really working, I like that. But, what can I get for free? So no credit. Yeah, but.
Wait, can you just run it?
I don't care if it's over that. And whatever you get, the last minute is quite long.
This one?
Yeah, one of them is really good.
Literally. Oh, 12?
I just wanted to spend figure.
You are?
Yeah.
It's not you, it's a
But everything was in the right unit, and then.
Because mine was 12 too. Was it just? The last year, it's the last line, last.
Hey, you messed it up for TWP. Are you serious?
That way I get.
I was like,
Yeah, I keep getting a message whenever I try to use the code.
So you do about
Oh, the top one, okay.
that's fine. Okay, this one is the, this is what I'm asking for here, right? And these, yeah.
But I have no mental capacity.
Oh, you were gonna go to the restaurant.
So that's, okay, I don't know what that symbol is. So I think there's a mistake there. Okay, so sigma times AX is not sigma divided by Alright, alright, now make sure you divide by 1,000. Yes. That's up your name, that's fine. Can you show me what it is, what it looks like? In the text? Just type it in. I'm sorry, okay, thank you. Alright, go ahead. So you don't want, you want to do it here, huh? Here, before the. So now you have, what is stress? Correct. Okay, so the force in your HV is X bracket.
Yes.
This is X bracket. X bracket. Yeah, go ahead. Like it's great, right above. Area, so now we have to calculate the area. So, what is the area? Right, so what's the area? So the second here is the what's the area? Alright, because I don't calculate it out, I have a computer calculate it. So I square pi. So now you have order operations, right? So you have to exercise everything. Now pi, so in this is equally dot pi. And
What makes more
now
sense?
you said radius squared. So e squared or d over c, right?
Okay, that's a cute name.
Well, you said it was or you said e squared over 4. E squared over 4 is e squared. So you're e
Well, you can just like, but I have to wait the bus.
squared is not e there.
Line P, right?
No, but you don't have to go bus.
No, it's still under.
Oh shit.
Now, this is an issue because this is in centimeters, right? So you can
Yeah, yeah.
How did you find, how did you know?
I can do it if you want. But
Take and then take out. You're not. It's just not everyone in the room. It's just in the out. For no reason. What is this? That is not.
In my head.
It's just me.
did it work?
Yeah.
Good.
Yeah.
Would you
Yes.
rather use it
Oh, I'd rather you.
Because I used to
everybody?
Professor, do you actually look at the attendance photos?
Yes.
Thank you.
Helps me learn who's in the class.
Okay. I just wanted to make sure that my efforts weren't in vain.
No, if there's any issue, send me a message in Canvas though.
Okay.
Like a direct message, like in the inbox.
You got it.
Okay, if there are any issues with the grading. How are you all doing?
We're good.
You're good? Okay, I guess class is over. I didn't even realize. Okay.
I can't think about it.
We need to also think.
Wait, that's it. That makes so much more sense. When I say it out loud, that makes sense. You need to. That doesn't make sense. It does make sense. You don't have to everything off.
Thank you. See you, Ahmed. Okay.